So we've been looking at limits. We've been looking at limits by looking at graphs and finding limits, and we've started looking at limits by algebraically. And so we're going to continue to look at limits algebraically. And let's go through some examples, lots of examples of that and things that you will see when you're doing your homework. We are going to skip 1.3 for now. Actually, it's 2.3, which is solving. It's actually, sorry, I'm trying to do too many things at once. I need to stop and actually just talk to you. So we will be skipping 2.3, which is limits and proving why a limit exists. We'll get into that next week, but we're going to continue just looking at limits algebraically, how to solve them, and tips on how to solve those. So let me share my screen with you. So we saw limit laws a couple of class periods ago and looked at limit laws and saw that we could do just direct substitution when we're finding limits. And so let's just go through this. And sometimes when we're doing direct substitution, it doesn't just work out right away, and we need to look at a couple of things. And I can't find my pen. Okay, so direct substitution and this property. So if P is a polynomial or a rational function and A is in the domain of F, then we know that we can look at the limit as X approaches A of F of X. We're just going to plug in our value of A wherever we see an X in our function, and that should be our limit. We got to be careful though, because if we're applying the substitution property and we get an answer in either the form of 0 over 0 or infinity over infinity, this is called an indeterminate, and this doesn't tell us anything about the limit. So if you get one of these cases, there's a couple of different ways that we can approach it and go back and find the limit. So one trick is to see if you can factor both the numerator and denominator and simplify like factors, and then take the limit. The other thing that could happen, maybe you have radicals in the numerator or denominator. And if that's the case, and you plug in and do direct substitution and get 0 over 0, then you're either going to want to try to rationalize the numerator or denominator, depending on where that radical is. So doing one of the above steps, usually get rid of the indeterminate form, and then we're able to evaluate the limit by that direct substitution. So let's go through and get some examples done. And just before I do that, just in time remediation, just in case you don't remember what it meant to be rationalizing either the numerator or denominator. So remember that the conjugate of, let's say, square root of A plus the square root of B. That was just changing the sign in between your two terms. So that would be the square root of A minus the square root of B. So we changed the signs between the two terms. The reason why this is helpful is because, recall, normally we went in this direction. If we had A squared minus B squared, that was a difference of 2 squares, and we could factor that, right? This was the same thing as A minus B, all times A plus B. So if we're multiplying, we're choosing the conjugate to be the opposite sign, and so when we're multiplying the two terms and its conjugate, basically that's a difference of 2 squares, and we can go the other direction, and we can just square the first term and then subtract off the square of the second term. Bring in an example. Let's say So let's say that we're taking the limit as y is approaching 0 of 5y cubed plus 8y squared, and that is all over 3y to the 4th minus 16y squared. Okay, so right away, we would just go in and we would do our direct substitution. This is y is approaching 0. Our variable, just y in this case instead of x. And so we're going to go in here and we're going to do our direct substitution. But notice that every single term in the numerator has a 0. And so raising 0 to a power is 0 times some constant is 0. So we going to get 0 in our numerator and we're going to get 0 in our denominator. Same reasoning. And so this again was that indeterminate form, and that didn't tell us anything. And so one way to go through is to try to simplify it to get it in the form so it doesn't give us that indeterminate form when we take the limit. So one of the ways is to see if it's factorable. And so if you look at both the numerator and denominator, notice that the numerator, we have 5y cubed plus 8y squared. So they have 2 y's in common, or y squared in common. So we can pull y squared out of both of those terms in the numerator. So we'd be left with 5y plus just 8. And then in the denominator, we have 3y to the 4th minus 16y squared. So they also have y squared in common. And so if we pull that out, we get 3y squared minus 16. Oops, sorry. So notice we both have a y squared in common. And so those cancel out. And now if we did a direct substitution and wherever we saw y, we replaced it with 0, we would get 5 times 0 plus 8 in the numerator, all over 3 times 0 squared minus 16. And so now when we simplify, we get 8 all over negative 16. And we can reduce that. I can pull the negative out front, and 8 goes into 16 2 times. And so we can reduce. And this gives us negative 1/2. So if you get something where you have 0 over 0, that's an indeterminate form that doesn't tell us anything about the limit. And we got to manipulate it so we can figure out what's going on. As in this case, y is getting closer to 0. What is that value we're going to get closer and closer to, which would in this case be negative 1/2. So any questions on that example? So what about the limit as h is approaching 0? I have the square root of 5h plus 4 minus 2 outside the radical. And then this is all over just h. So first, again, always try direct substitution. And so wherever we see an h, we're going to plug in 0 and see if that gives us anything back. And if we do that, we get 5 times 0 plus 4. And then outside the radical minus 2 all over 0. Well, 5 times 0 is 0. So really what we have underneath that radical is square root of 4 and minus 2 all over 0. Well, square root of 4 is 2. So in the numerator, we have 2 minus 2 all over which is 0 all over 0. Okay, so again, indeterminate form doesn't tell us anything about the limit. We need to go back in and manipulate. So this case, we can't really factor. And so, but I do notice that we have a radical in here. And so we can clear a radical. We can rationalize the numerator in this case. And so to rationalize the numerator, again, we're going to multiply in this case by a fancy 1. And that fancy 1 is going to be the conjugate of what our numerator is. So we're just changing the sign between that radical and that 2. And so the conjugate in this case is the square root of 5h plus 4. Change the sign in between. So we're going to get that going to be my plus in between and then 2. So just multiplying by a fancy 1. And so let's go through here, and we're going to use this fact that we were just talking about. If we're multiplying by the conjugate, we can just square the first term and square the second term. And you're going to be doing that a lot. And so try to get out of the habit when it's a difference of squares like that, the foiling it out. Just notice that that is a difference of squares. We're just going to square the first term. So square root of 5h plus 4, quantity squared, minus and squaring the second term. So 2 squared all over. Let's not distribute the h in the denominator. So let's just leave it with that factor. Square root of 5h plus 4, and then outside plus 2. So if we square the numerator, squaring that 5h plus 4, the square root of that, squaring that gets rid of the radical. You're left with 5h plus 4, minus squaring the 2, we get a 4. All over h all times the square root of 5h plus 4 plus 2. So notice we have like terms in the numerator, 4 minus 4, so that cancels. And we have 5h all over h times square root of 5h plus 4. And then outside of the radical plus 2 in parentheses. So technically, if I did direct substitution right now, I would still get 0 over 0. But notice that my numerator have h as a factor and my denominator has h as a factor. And so those actually we can cancel with one another. So now we're technically, by simplifying and manipulating, we have the limit as h goes to 0 of 5 all over the square root of 5h plus 4 underneath the radical, outside the radical plus 2. So direct substitution, we're not going to get an indeterminate form anymore. So plug in 0 wherever you see an h. So we get that's equal to 5 in the numerator all over, well, with the 0 down in that radical, we really are just left with 4 underneath the radical. So square root of 4 is 2 plus that 2. So we get 5/4. So that limit as h approaches 0 of that function is 5/4. So I just want you to be aware when we got 0 over 0, that was an indeterminate form. But there's a difference. Like if you were looking at a limit, let's say as x is approaching a of f of x, and you got something in the form of 0 over a number. Okay, so let's just call it b. Where b doesn't equal 0, That's not an indeterminate form. This, remember, is equal to 0 over a number is 0. Or let's say we were doing this limit as x approaches a of some function g of x. And let's say you plugged in, x equals a n for x into that function, and you got something in the form of, let's say, b over 0. Again, b can't be 0, because if it was 0, that would be indeterminate. But recall, we can't have 0 in our denominator. So if that is a number other than 0 in our numerator, this is undefined, or the limit does not exist. That's another way to say this. So I just wanted you to be aware of that, because sometimes students will see this then and either think it's an indeterminate, or they'll see the indeterminate form and think it's undefined, or the limit doesn't exist. So I want to do one more example where we need manipulation. I have problems in front of me on my screen, so let me grab one. There we go. Okay, so in this example, we're looking at the limit as x is approaching 1 of, in the numerator, I have x raised to the -1 power minus 1 all over my denominator, which is x minus 1. Okay, so let's actually first rewrite this. We could leave that negative exponent there, but I would prefer to rewrite that. And so just recall again, let's say you have b raised to a negative exponent. We can change that exponent and make it positive. If this was in the numerator, I could rewrite this as 1 over b to the nth power. And so when I have this x to the -1 power that I see of this function I'm taking the limit of, we can rewrite this as 1 over x to the first power, but I usually wouldn't write that. So just rewriting this with a positive exponent, this is the same thing as the limit of 1 over x minus 1 all over x minus 1. And I can't just throw that x down in that denominator here, because I have more than one term up here in this numerator. But now notice when we do direct substitution and we plug in 1 wherever we see an x, we're going to get 1 over 1 minus 1 all over 1 minus 1. And so we're getting that indeterminate form again, because 1 over 1 is just 1. And so we have 1 minus 1 in the numerator, which is 0, all over 1 minus 1, which is 0. So if you have a complex fraction, so remember, complex fractions are fractions within fractions. If we rewrite it to get rid of the complex fractions, then that maybe will help us to get rid of that indeterminate form. So there were a couple of ways in algebra that we could get rid of complex fractions, or rewrite complex fractions so that they didn't have fractions within fractions. Personally, there's the method I tend to prefer is clearing the fractions within the fraction by looking at the LCD, the least common denominator of all the fractions within, and multiplying by a fancy 1. And so if I look at my numerator, I have a fraction within my numerator, right? Just 1 over x. And if I look at my denominator, I don't have any fractions there. And so my LCD is going to be, of all the fractions within my fraction, is just x. So my fancy one that I'm going to multiply by is going to be x over x. And the reason why I choose that least common denominator is I know when I start to distribute, that fraction is going to cancel out. And so if you multiply 1 over x by x, well, the x's cancel, right? And just leaves you with a 1. And so I would just be left with 1 in the numerator when I distribute for the first term. But if I multiply x times -1, well, -1 times x, that's going to be a minus x there. All over, and so let's distribute x to both terms in the denominator. And actually, I believe if we don't, let's not distribute it. Let's just leave it outside. Just because if we do distribute it, we're going to have to go back and factor it out later. So let's just keep the x there and then times x minus 1. Unfortunately, if I go back in here and I do my direct substitution and I plug in 1 for x, notice I get 1 minus 1 in the numerator. That's 0. All over 1 times 1 minus 1 in the parentheses. So 1 times 0, which is 0. So notice what we have in those parentheses in the numerator 1 minus x and what we have in that denominator x minus 1, those are almost identical. They're just off by a -1. So I technically can pull out a -1 from one of those. So maybe let's just factor a -1 out of that numerator. So if I pull out a -1 from that numerator, my first term would be -1. And my second term would be plus x. All over x, all times x minus 1. Order of addition of 2 terms, it doesn't matter. And so -1 plus x is the same thing as x minus 1. So you can rewrite that like that right now, or if you see that, just cancel them out. And so we're just going to take now the limit as x approaches 1 of -1 all over just x. And so if we go through and we do our direct substitution now, wherever we see an x, we have -1 in the numerator all over 1. So this is going to equal -1. So if you have a complex fraction and you're taking the limit, you get 0 over 0. Try to manipulate it by getting rid of the fractions within the fractions. Okay, so in this next example, we have the limit as x is approaching 0 of the function 2 sine x and then -1. And so again, all we're doing is direct substitution. We're going to plug in 0 wherever we see an x. And so when we do that, we get back 2 all times sine of 0 minus 1. Well, sine of 0 is actually 0. So we have 2 times 0 minus 1, which gives us back -1. Okay, so if you remember and recall what we're doing, as you're getting closer and closer to 0, and if we looked at the graph of 2 sine x minus 1, it's telling me that my y value that I'd be getting closer and closer to is -1. And I just kind of want to talk about this just kind of as a recall of, because you really should be familiar with what your functions look like. And so if we were to graph y equals 2 sine of x minus 1, remember the number in front of your sign, this 2, this affected our amplitude. And so if I was just looking at 2 sine of x, that would have been, my max point would be 2 and my minimum point would be -2. So I know amplitude is 2. But that -1 does a shift in our graph. There's -1 here. That's shifting our graph down 1. And so I would think about my picture. So here, normally it would have been 2 and -2. I don't have any, my period is the same as 2 pi. There's no, shifting, no phase shifts in the graph. And so let's put it on the important points here, like pi halves, pi, 3 pi halves, 2 pi. So negative pi halves, right? Negative pi, negative 3 pi halves, negative 2 pi. We can think of it as our midline as our x-axis, but if we shifted everything down 1 unit, I don't know if you guys remember this, but we shift everything down 1 unit, we're going to think of that line y equals -1 as where we are crossing. And so shifting it down, my min value is actually at -3. I know sine starts at the origin, but shifting down 1, I'm on that midline of y equals -1. Sine then goes to positive, and I'm going to hit my max at pi halves, but I shifted down 1 is now at a +1. At pi, I'm going to reach 0 normally, but shifted down, so -1. 3 pi halves is going to go to my minimum of -3, 2 pi's up here. So negative pi halves, that's going to be downwards to -3, up. Okay. So graphing this, if we looked at what's happening as x is approaching 0 on this graph, coming in on the left and the right, notice our y value that we're getting back on this graph is -1, which we just showed here algebraically. Okay, so that was a little review of graphing of trig functions and looking at shifts of a graph and recalling what is happening graphically as you look at limits. So now our example says the limit as x is approaching 0 of the quantity x squared -1 all times the quantity 2 minus x. So let's go through, let's do our direct substitution. And so if we do that, we're getting back 0 squared -1, that whole thing times 2 minus cosine of 0. Well, 0 squared is 0 minus 1, so we have -1 left in our first parentheses. And then 2 minus cosine of 0. Cosine of 0 is 1, so 2 minus 1 here. So we really have -1 all times +1, which is -1. Okay, so the next example, we're actually given information about a limit and what it's approaching, actually 2 limits. So we're looking here at the limit as x approaches 4 of f of x is equal to 0. So we're given that, and we're given that the limit as x approaches 4 of g of x is equal to -3. So for part A, it wants us to find the following. We're looking at the limit as x approaches 4 of g of x plus 3 inside parentheses. But recall by those limit rules, if we had a sum of 2 functions and we're looking at the limit, we can look at the limit of the first function. So we could rewrite this as the limit as x approaches 4 of g of x plus the limit as x approaches 4 of 3. Well, we're given up here what the limit as x approaches 4 of g of x is. And so we can replace that with -3 plus, remember the limit as x approaches a number of a constant was always just equal to that constant. And so the limit as x approaches 4 of 3 is just 3. And if we sum -3 plus 3, we get back 0. So that was A. So for part B, same sort of reasoning using those limit laws. We can break this up. We have the limit law that if you have a limit of something going, x going to a number of a function times another function, we could look at the limit as in this case, x approaches 4 of the first function, g of x, all times the limit as x approaches 4 actually. The first function was x in this case. All times the limit as x approaches 4 of f of x. So a limit as x approaches 4 of x, that was just 4 times, well, we're given over here that the limit as x approaches 4 of g of x, that's equal to 0. And so in this case, we're going to multiply 4 times 0, which again gives us back 0. So you might be given information about limits and then asked to find other limits using those properties. Okay, so our next example is based off the following. So, and this is what we talked about with the first section we got into when we were starting to talk about calculus, about rates of change and average rates of change. And so this states that because of the connection with secant lines, tangent lines, and instantaneous rates of limits of the form, the limit as h approaches 0 of f of x plus h minus f of x all over h, occur frequently in calculus. So in these examples, we're going to evaluate this limit for the given value of x and the function of f. Okay, so we are trying to look at, we're looking at the limit as x is approaching -2, but actually, sorry. We're going to look at h goes to 0 of f of x plus h minus f of x all over h. Okay, so recall, this is just telling me I'm plugging in an x plus h, this first piece, f of x plus h, wherever I see an x and f of x. And so sometimes it's helpful just to do it on the side and then pull it in. And we'll just do that for now. And then we'll get good where we don't have to do that anymore. So going to my f of x function, I see an x, so I'm going to put parentheses and then I'm going to square it. So I'm looking at x plus h quantity squared. Okay, so I need to expand that out, x plus h times x plus h. And if I distribute and combine like terms, you're going to get an x squared. You have an xh plus an hx, so that's really plus 2xh plus h squared. If you're looking at the next piece, minus f of x. Well, minus f of x, all you're doing is you're distributing -1 to your f of x terms. And so all this is -1, right? All times f of x, which is x squared. So let's go back and plug in what we just found for our numerator. So the limit as h approaches 0. We saw that this f of x plus h value is the same thing as x squared plus 2xh plus h squared. And then we saw that minus f of x. So that's minus x squared. And then it tells us to put that whole thing over h. So let's combine like terms in the numerator. So we're looking at the limit as h is approaching 0. Well, notice I have an x squared minus an x squared, so those cancel with one another. And I'm left with 2xh plus h squared all over h. So I notice right away, if I plug in 0 wherever I see an h, I notice right away that I'm going to get 0 in the numerator because both terms have 0 and 0 in the denominator. And that gives me that indeterminate form. And that's where I had to go back and manipulate. So we can factor out an h in our numerator. And that would leave us with a quantity 2x plus h all over h. And so notice we have a factor of h that cancels. And so really we're looking at the limit as h goes to 0 of 2x plus h. So if we go in and we plug in 0 wherever we see an x, not an x, an h, this would just give us back 2x. So if you've had calculus before, you've actually gone through the easy way probably or now and know how to take the derivative. We actually just took the derivative of that function, but we'll talk about that more in the next chapter. And you should see that the derivative of x squared is 2x. But this wanted me to evaluate this when x was negative 2. And so when x is negative 2, and if we go back and plug that in, we were going to get back that this is negative 4. If you looked at this graph, technically all that's saying is our graph of x squared, we know is a parabola. And what's happening at x equals negative 2 is that our slope right here on that line, the instantaneous rate of change at x equals negative 2 is equal to negative 4. So the slope here is negative 4. Which makes sense if you look at that parabola that's decreasing there at x equals negative 2. And you can, so it's good that our slope is negative. If we had gotten it positive, then there would be something wrong there. Let me pull one more out. How about let's do the same thing, but this time our function f of x. Our function f of x, let's say, is the square root of 3x plus 1. And we want to find the limit as h goes to 0 of f of x plus h minus f of x all over h when x equals 0. And so we want to do it in pieces. And if you had just gone in here and you plugged in 0 wherever, let's just not do that. If you plugged in 0 wherever you see an x, things would have given us 0 over 0. But let's just go in and plug this in. So again, this x plus h, f of x plus h, that's saying go back into your function f of x and plug in that x plus h wherever you see an x. I'm just going to bring down my limit. is h goes to 0 of the square root of 3. I see an x there, so I'm going to put parentheses. I'm going to go back and replace that x plus h there, plus 1. And then we have minus f of x. So minus our f of x function. Well, f of x function is this square root of 3x plus 1 all over h. Unfortunately, if we plug in 0, wherever we see an h in here, notice that numerator is going to give us the square root of 3x plus 1 if h is 0 minus the square root of 3x plus 1. So we're going to get that indeterminate form again if we go in and plug in 0 wherever we see an h. So we got to manipulate it. And the way that we manipulated it, we saw that if we multiply by the conjugate, that could help us out. So we're going to multiply by a fancy 1, and that fancy 1 is going to be the conjugate of that numerator. So that would be our first radical. So 3 times the quantity x plus h plus 1 underneath that radical. Change the sign in between. So now it's going to be plus the square root of 3x plus 1. When I multiply the numerator by, I also have to multiply the denominator by. Okay, so we're technically multiplying by the conjugate, and we're multiplying by a difference of squares. So we can think of it as just squaring our first term. Well, if we square that first term, right, it's just going to get rid of that radical, leaving you with 3 parentheses x plus h plus 1 minus, if we square our second term, you got to be a little bit careful because there's more than one term underneath that radical. But if we square that second term, we're just left with what's underneath the radical. So I need to put parentheses around that whole thing. Parentheses 3x plus 1 all over my h. And I'm not going to distribute my h. I'm just going to keep it as all times 3 times that quantity x plus h and quantity plus 1. Outside radical plus square root underneath the radical 3x plus 1. So let's simplify our numerator, and things are going to start to cancel out really nicely. And so notice when we distribute that 3 inside the parentheses, we get 3x plus 3h plus 1. And let's distribute this negative to each term inside the second parentheses. So that's going to give us minus 3x minus 1 all over h times that parentheses, 3 times x plus h plus 1 plus square root of 3x plus 1. So things cancel. 3x minus 3x cancels. 1 minus 1 cancels, and we're left with 3h in the numerator, all over h times parentheses. 3 times x plus h plus 1 plus square root of 3x plus 1. Again, I noticed I would get 0 over 0 because I have a factor of h in the top and a factor of h in the bottom. So let's cancel that out. And so now if I do direct substitution and I plug in 0 wherever I see an h, I'm left with just 3 in the numerator, all over the square root of 3x plus 0 plus 1 plus the square root of 3x plus 1. So let me just simplify. So this is 3 all over the square root of 3x plus 1 plus square root of 3x plus 1. And notice that's the same radical. So I can rewrite that as 3 all over 2 square roots of 3x plus 1. Almost there. We wanted to know what this was when x was equal to 0. So just go in here and plug in 0 for x. And if we do that, we get 3 all over 2 square root, well, 3 times 0, 0 plus 1, so square roots of 1, or 3/2. So the instantaneous rate of change when x equals 0 of that function, f of x equals the square root of 3x plus 1, would be 3/2. So slope of the tangent line, another way to say that, the slope of the tangent line at x equals 0 is 3/2, or the instantaneous rate of change at x equals 0 is 3/2. So all those mean the exact same thing, but just stated a little differently. So we just completed 2.2 in the textbook. That's the only section that we covered this week in class. And so that will be the only homework that is due on Monday next week by 1 p.m. so that it's not late. I have moved already 2.3 to be the following week. I will move 2.4 also. So it's not reflecting that it's due on Monday in a minute.